your tree is going to be different. Probably is going to be different. And therefore there is a high variance because there's a high differences between the two of you. Okay? So the procedure with low variance will yield similar results if applied repeatedly to distinct data sets. Which means that if we choose a procedure with a low variance, it doesn't matter whichever sample that you choose, your tree is going to be the same. And therefore, we would apply methods such as the bootstrap, aggregation, including backing. Okay? So how to reduce this variance, and therefore we would predict that we would increase the prediction accuracy. Number one, we can take as many training sets as possible. Okay? And then we build separate prediction model, and then we average the resulting prediction. So maybe you just randomly choose different training sets, and then you build the predictive model, and then we average them all. However, this is not practical because we do not have the access to multiple training sets. Okay? So, what do? We take the bootstrap, which is we take repeated samples from the single training data set. So basically this, we cannot have like different training data sets, but from the same sample, we can take repeated samples from this population, okay, from this training data set. And then we can generate different bootstrap training data set. We call it B. So this is like B1, B2, B3, okay? And then we train our method on the B bootstrap data, and then finally we average all the prediction. So this is the functions of the bagging is given by the average of all the summations of all the truths from B1 until B. And this process is called bagging. It's not so much different from the bootstrap. So bagging has been demonstrated to give improvements in accuracy by combining hundreds or even thousands of the trees into a single procedure. So bagging, number one. What is bagging? You run the model on repeated samples from the same training data set, and then you take the average. This is bagging. And for the classification tree, okay, we record the class predicted by each of the B tree, and we take the majority, which means that instead of taking the average, but we look at what is the highest frequency. Okay, so that will be the B result. Okay, so OOB error estimations. Okay, so this is out of the bag observation. Okay, so let's say we choose 2/3 of the samples to become our training observation, and 1/3 is the out of the bag observation. Basically, this is just, for me, if you ask me, this is just like a different terminology. Okay, if you see, 70% is used for training, 30% is used for testing. Out of the bag is like the testing data set. Okay, so we predict the response for the observation using each of the three. Okay, in which the observation is OOB or out of the bag or the testing data sets. And then this yields B divided by 3 prediction for the ith observation, and then to obtain a single prediction for the ith observation, we average the predicted response, or we compute the OOB of the MSE in the regression case, or the classification error in the classification case. Basically, this is just like the testing data sets. Yeah? So now let me talk about the variance importance measure. So of course, if you look at this, because trees are non-robust, each one of you will have a different tree. Okay, when you use a different sample from the training data set. Therefore, bagging can improve the accuracy compared to a single tree. However, it can be difficult to interpret the resulting model because you no longer have that this splitting, these regions, and all that. Yeah? So it's no longer clear which variable are most important. Because every time that you run this bagging, okay, this bootstrap method, probably the first one will say, okay, years is the most important. Second one say, no, kids is the most important. So, it's quite to, if that is your goal, interpretation is your goal, then I think bagging would not be suitable. In fact, none of this random forest bagging or boosting would be suitable. But if you don't care how to interpret it, but what I want is just a predictive accuracy, then yes, this method might result in a better accuracy. Okay, so I'm not going to talk about all of this. Maybe you can read in other time. Now let me skip to the random forest. Okay. What is the difference between bagging and the random forest? So let's say there is only one very strong predictor in the data set. Okay, usually this is the case. Yeah? You want to predict something, usually there's the strongest factor that could explain the large variation in the response variable. So, in the bagging method, most of the tree will use this strong predictor into top split. Because let's say this predictor explains like maybe 60% of the variation in the response variable. So what happens in the bagging is that it will always be chosen as a top split because it has a very high explanatory power. Okay? Therefore, all the bagged trees will look quite similar, which also means that they are highly correlated. Okay? And therefore, this is the difference of the random forest. Because random forest, they overcome this problem by forcing each split to consider only a subset of the predictors. Now, look at this difference here. Bagging, they only consider subset of the responses. Subset of the observation. And they run it many times to get the average. In the random forest, it considers subset of the explanatory power. So let's say you have x1, x2, x3. So maybe during the first one, you only consider x1 and x2. Second one, x2 and x3. Okay? So let's say x1 have the largest explanatory power. So in the second model, where x1 is not included, so they will choose either x2 or x3. Okay? So if x1 is very powerful, even if you run a random forest, you run many trees, x1 will still appear as the most important. But we also consider what if. Okay, what if? So that is the difference between random forest and the bagging. Now, boosting. Boosting, it works like bagging, except that the trees are grown sequentially. Okay? In the bagging, you just grow the trees, just they become a tree. Okay? In the boosting, each of the tree is grown using information from previously grown tree. So let's say you like planting, right? So you have a plant here, and you grow the plant. Suddenly you look at your plant, oh, it's too small. Okay, and the flower doesn't come out. So you learn from that information. You say, the next tree that I'm going to make is I need to put more fertilizer. Suddenly the tree dies. You say, okay, now I learn my lesson. Maybe not too much fertilizer, a little bit fertilizer and more water. So you use all this information. Eventually you're going to get a better tree. Yeah. So this is how boosting works. So the boosting, it does not involve the bootstrap sampling. Each tree is fit on a modified version of the original data set. Okay, so you learn in the original data set and then you improvise. So given the current model, we fit a decision tree to the residual from the model. Okay, so we take what's wrong with the previous model, we learn from that and we do better. And then we add this new decision tree into the fitted function in order to update the residuals. Okay, so now there's a difference between bagging, random forest, boosting. Bagging, you just run many trees, take average. Many trees using different samples, take the average. Random forest, I forgot. I'm already tired. Okay, random forest is you choose, you build many trees, each time you forget about one predictor. Okay? Boosting is when you learn from the mistake and you improvise. Learn mistake, improvise. Okay? So that is the basic difference between these three. And that's the end of the task. Not yet. We go for the coding. Okay? Do we want to have a break or do we want to just continue? Just continue, yeah. We can go home and sleep. Okay, for this one, we need to have a library of 3 Okay, if there's no tree, we can install the packages. Once we install the package, then we can download the library tree and also the library of ISFR. Okay, and we can attach the data. We're going to use CASIS data. In order to learn what is CASIS data, we can just question mark CASIS, and we can read the descriptions of the CASIS data on the right hand side. Okay, for this one, let us start with the regression tree first. I hope you have already read the documentations of this one, yeah? So you can look at this one. So we want to look at the sales. Where is sales? Sales is over here. Okay. So let's say we want to have a summary of sales. So the sales is from 0 to 16. Okay. Start with the classification tree. Let me go to that one. Okay, I think we start with the classification first, yeah? I think this example is classification. Because classification, it requires the use of categorical data. So we're going to recode sales to be categorical. Okay? So we have, we call it high. High is, if else, sales is less or equal to 8. Okay? No. If yes, then it's going to be yes. And then we want to change it from character to factor. Okay. So now we type in class of CASIS high. You can see that it is a factor. Now we want to develop a classification tree. Okay, so we call it, maybe we call it T1, yeah. T1 is equal to tree of high on the rest minus sales. Okay, data equal to car 6. This one means that a high is run on everything except sales. The variable high is run on everything except sales, where the data is car seats. And first we get the summary of T1. Now let's look at the summary of the output. Okay, so basically how many variables are chosen? 8 variables. Okay, 8 variables are chosen. Originally in the data set we have 11 variables, only 8 variables are chosen. Chef location, price, income, population, age, US, etc. How many terminal nodes are there? 27. 27 terminal nodes. Which means that this is a very big tree. Okay? And because this is a classification case, we look at the misclassification error rate, which is 0.09, which is good. Okay? 0.09 is very low number. It's good. Now we want to show this tree. Okay, so we use the plot functions of T1. So first it's going to have something on the right. It's just the branches. Okay, now we want to add the text, and we put pretty equal to 0 just to make it pretty. You can just change this, yeah? Alright, so you can just zoom on the resulting output. Now let's look at the output, yeah? I'm gonna make it bigger. Now you can make this bigger, yeah? As we can see here, we cannot really see. It's 27. It's too big here, yeah? 1, 2. If you compute all the terminal nodes, you know that 1, 2, 3, 4, 5, 6. Everything will be 27. So this is a 27 terminal nodes, where the most important variable is the chef location. Okay? And then the price and etc. Now, if we look at this, we are able to see, especially the top split. Yeah? If the chef location is bad or medium, you go to the left side. And then you look at the price, and so on and so forth. But as the tree gets bigger, sometimes it's difficult to see. So the way that you're going to interpret, you can just type in T1. Okay? You type in T1. Okay, this one looks, yeah, it looks a lot. But let's see. At the root, it starts with 400 observation. Okay, start with 400 observation. All right. And then the first clip is at chef log, okay, where 68% says no, okay, and it involved 350 people over here. And after that, it's further split to the price. If the price is less than 92, it goes there. If the price is larger than 92, it goes here. So it takes a little bit of, peeking into this to look. So everything with the star means that it is a terminal node. Okay, so this is terminal node. So this is terminal node. If the comp price is less than 110, then it is a no. If the comp price is larger than 110, then it is a yes. Okay, so this is like as you can see here, if this one is larger than this one, 0.59 is larger than 0.41, then it is a no. Means that majority says no. Okay. This one also, you can see that 0.98 and 0.31. If this one is larger, then it is more like no. No is larger. Okay. But if 0.3 is less than 0.6, then it is more yes. Yeah. So all the stars are the terminal node. So this is how you interpret this one. In case it's difficult to see in terms of this graph here. Okay, so this is just we run the tree on all the 400 observation. And now we want to evaluate the performance. I'm going to make this smaller again. Evaluate performance. Because we want to have similar results, so I suggest we use set.c. Okay. And training data set is given by sample 1 to the number of row of car seats, which is basically 400, and we want to choose randomly 200, which means that half will be chosen as the training and the half as the testing. Okay. Now, testing data set, I just use this one smaller. Testing data set is equal to car seats, okay, minus all the training data set. So this is testing data sets, yeah. And now we want to develop this tree, okay. We call it T2. T2 is tree high on everything except sales, okay, using the car seats data, but we have a subset which is training data set. Now we want to predict, okay, we call it predicted. Predicted is we predict based on T2 on the testing data set. Type is, because this is a classification, type is class. Okay? So for each of the testing data sets, we predict whether it's going to be yes or no. Now we want to tabulate between the predicted this one car 6 based on the testing data set. Let me check answer. Yep, sorry. I just shouldn't put a comma over that. So this one, okay, how many misclassification? Yeah, 13 plus 33 divided by 400. Is it 200? 200. I believe it's 200. So the misclassification is at 0.23. Now let's do pruning. Okay. Pruning. First we set seed, okay. And then maybe we can call it CV cascade. Okay, is equal to CV.3 of the T1. Okay. T2. I think we just do on T2. The function is equal to prune for misclassification, because this is a misclassification set. When we type in cv.carseed, so first is this is the size. For the size of 21. The deviance is 74, okay, and then the rest of the information here. Now let's look at this one. I think it's quite difficult to read from the numbers here. Okay, so let's draw a graph. So Qua and Pro shows that they changed the graphic parameter to have 1 times 2 windows of graphic parameter, which means that you put 2 figures in just one window. Okay, and then we can just type in plot of CV car6, the size and the deviance, type B, and then the other one is the K and also the deviance, type B. And then you're going to see on the right hand side, yeah, so you can just make it bigger. graph here. Let me just enlarge this one. So this is the deviance. The vertical lines is the deviance. And you can see that the lowest one is when the size is 9. Okay. The lowest one is when the size is 9. So we would choose 9 as our, Okay. I think something to do with the set of C. This one is not the same. Okay, so now we know that instead of 27, okay, we can reduce the misclassification rate. Remember what is the misclassification rate before? 0.23. Okay, remember this figure, 0.23. Right? Now we want to prune the tree. So how do we prune the tree? Okay. We call it prune, okay, which is using the prune dot misclass, okay, of T2 best equal to 9. Best means that the best or the optimal size is 9. Okay, again, far and fro, C. This one we just want to change the window back to only, okay, only one graph. Then we can type in the plot of the prune cosets of prune and text of prune pretty equal to 0. Now what you can see on the right hand side is the prune tree with only 9 terminal nodes, which is much simpler. Okay, but how about the misclassification rate? We need to make sure that the misclassification rate is lower or better than 0.23. Okay. Now we have prune predict is using the prediction function of prune. Okay. T2. I mean this one is T2. Type class. file stage, not batch 6. Yeah. I might miss up the coding from the lecture note, so that's why I have to check it again. Table of product trading. No, I made a lot of mistakes already, I hope. Okay, please bear with me. Yeah? Okay, so the misclassification here is 20 plus 25 divided by 200. 0.22. Okay, which means that it is better. Okay, so 3. This is 3. I put there N27 means that there are 27 terminal nodes. Yeah. Misclassification is 0.23. Now this is the prune one. N is 9. Okay. Misclassification is 0.225. So this one, the prune one, is not only simpler, but it also have a less misclassification rate. So of course we would like to have this one instead of the more complicated ones. Okay, now I just want to, any questions so far? Everyone is okay? Not okay? If this one doesn't work, I think probably you need to run it again based on the lecture, okay? Anyone have questions? to the regression tree. I think this one is a bit simple, yeah? Regression tree when the response variable is numerical. For this one, we need to use library mass set.c.1. Okay, the training data set is the sample from one to the number of row of the Boston data set, and then the number of Boston data set divided by 2 because we are not sure how many are there. Okay, and then the tree.Boston is equal to tree of MACV. We run on everything. Okay, data equal to Boston, and the subset is string. Subset is string data set. So first is we can plot the tree.Boston, and then text of tree.Boston pretty equals 0. Okay, so how many terminal nodes are there? If you look, they have like 7 terminal nodes, but the picture shows that RM is the highest. Okay, is the most important part. Now let us just go straight to the pruning. The pruning is CV Boston is equal to the CV.tree of the tree Boston, and then we plot the CV.Boston. First the size, then CV. Boston, the deviance times B. Now, if we look at this graph here, some of us might have different, a different interpretations on this one. But probably because of the way the sampling is done. Yeah? So here we see that the minimized deviance is at 6. Yeah? Let's choose number 6. I think in the textbook it says 5. Yeah? But here I choose 6. Because 6 is further reduction. 7 no longer improvement. So now we see that it is at 6. So what I do is I do the prune Boston equal to the prune.tree of the tree.Boston, where I use best equal to 6. Now I put the plot. This is a little bit different from the textbook. Prune Boston. And then text from Boston pretty equal to 0. Okay, so this is based on 6. Now let us do the prediction. Calling y hat. Y hat is the predicted value. So y hat is predict based on the 3 Boston. New data is equal to Boston, which is minus the training data set. Minus training means that this is a testing data set. So Boston.test is equal to Boston of the testing data set on the variable med v. Now we can plot the y hat and Boston.test. Okay, you're gonna have a figure on the right hand side. So we just add the line there from 1, 0 and 1. So this is the regression line. So it shows here that it shows a good picture basically. If I'm going to make this bigger, it's easier to okay. This is okay. This is the true value, okay, of the Boston testing data set, and this is the predicted y, the predicted response variable. This is when predicted is 10, 15, some values here, and etc. So what we are interested in looking at is the MSE. Yeah? So to compute the MSE, we get the mean of y hat minus the Boston in the testing data set squared. Okay, so the MSE is equal to 35.28. Now, we've done both the classification tree and also the regression tree. Now, let me teach you how to do the bagging and random forest. Both will be using the same package. So first, we have to install packages, random forest. After that, you have the library random forest. Okay. Now I want you to recall the difference between bagging and random forest. Remember bagging, it's like a bootstrap where we consider all of the predators. We consider everything in every time that we do the tree. Okay. Random forest is that we try to, let's say we have like 10 predators. Okay. So, tree number 1, we remove 1. Tree number 2, we remove another 1. So we don't consider all 10 every time. Okay? So remember the difference when you do this coding. So first, we start with bagging. Okay? In the bagging, you put the bag of Boston, okay, using random forest. Bagging is using random forest. Yeah? Make V on everything, okay, where data is Boston, and then the subset is string, MTRY equal 13. What is MTRY? MTRY is, so this is what makes bagging different from random forest. Because MTRY says that for each time we develop the tree, we have to use or we have to consider all the 13 predators. Okay? We have to consider all the 13 predators. Whether we choose them or not doesn't matter, but we consider all of them. So this is bagging. Yeah? Importance is equal to true. Okay. Now we type in bag of Boston. Let's see the result. Number of trees, because this one we just use default. The number of trees, 500. Number of variables tried at each split is 13, because we see MTRY must be equal to 13. So this is mean of square residual is 11, and the percentage of variance explained is 85. Okay. So remember all this, yeah? Remember all this. Result. Now we want to do the prediction, and probably from there we can compute the MSE. Okay, first is we get y hat of bagging is equal to use the predict function bag of Boston based on the testing data set. Okay. And then we can compute the MSE, which is given by y hat minus y hat of bag minus Boston dot test square. So the MSE is 23. Okay. MSE is 23. this with random forest, compare with random forest, so we call it RF. RF Boston is random forest, maybe on everything data equal to Boston. Okay. Subset equal to train. MTRY is 6. Every time we want to develop the tree, we only consider 6, not 30. Okay. Importance is true. And then we can compute the predicted value of the RF given by the predict of RF.Boston. New data is Boston testing data set. And we compute the MSE. Okay, so MSE actually shows a reduction. Compared to begging, random forest shows a better prospect. It's 20 compared to 23. Okay, in the lecture note, there are many things that I do after this. Yeah, I look at the variable importance, and then some other things which I think you can try to do it in your own time. Okay, but now I just want to show this one. I think this is quite interesting, especially if you do the tree analysis in your project. Yeah, so you can use this one, var important plot of RF.Boston. So this one, it will result in the variable importance. Yeah. So this one you can look at the lecture notes, but I just want to show you this one a bit. So the most important variable, okay, whether you're using the MSE or using the node priority, I think it's not so much different. Okay. The most important is the RM rule, and after that we have L step, which is, you know, and then this is crime age. Okay, maybe this one it pick up the PT ratio and then knocks this, so that's a little bit different. Okay, but according to MSE, this is the variable importance that is the variable importance according to the node priority. So based on this one, as you can see, in the purity, now I want you to see the difference here between this, which is more scattered, and this, which is more like 2 of it is closer to the highest number, the rest of it is closer to 0. Okay? Because in purity, we try to get this purity, like whether you are this part or you are this part. Okay? And there's a few more coding for other kind of graph, which I believe you can do it on your own. Okay? So I think that's all for today. Yeah. The rest I think you can just run it in your own time. So anyone who want to ask any question, please come in front. Otherwise, thank you all, and the class finished. You can leave the class. Thank you.